Hello and welcome. My name is Liang. In this presentation, I'll introduce our paper, Semi-Supervised Neural Proto-Language Reconstruction. 19th century European philologists discovered that languages change in systematic ways, and by leveraging these systematic patterns, we can reconstruct ancestral languages called proto-languages. This method is known as the comparative method. The task we look at in this paper is protoform reconstruction. Essentially, we want to predict common ancestral words called protoforms based on their descendant words called reflexes. For example, the protoform wicinum in the proto-language Latin descended into reflexes in various daughter languages. We call sets of related reflexes cognate sets. So in this case, the input is the cognate set, and the target output is wicinum. The comparative method has a core assumption, the regularity principle, which states that sound changes are regular and that reflexes should be derivable deterministically from protoforms through a series of sound change rules. However, looking at a large number of cognate sets and complex combinations of sound changes can impose a heavy cognitive load, making the comparative method difficult for humans to apply in practice. Unsurprisingly, computational linguists have developed models to automate this process, with many recent works using sequence-to-sequence neural networks similar to those seen in machine translation. Since reconstruction maps from multiple daughter languages to one common proto-language, the input is usually represented as reflexes concatenated together with some separators and language identifier tokens in between. These models are trained with full supervision, meaning that for each input cognate set, there is an associated Go protoform label. But in a realistic scenario, historical linguists don't start by having a protoform for every cognate set. Instead, early on in a reconstruction project, there's likely a limited number of protoforms to work with. Thus, we introduced the task of semi-supervised protoform reconstruction, mirroring this exact situation. In machine learning terms, the labels are scarce. Ideally, we would want to make use of the unlabeled cognate sets during training, as they can be very useful in some situations. In this hypothetical illustration drawn from Tankulic languages with the first two cognate sets labeled and the other two unlabeled, a naive supervised model trained with only the label data would arguably predict U when seeing U and U in Guoshu and Ukro. However, taking into account the unlabeled examples, we see that if we predict U again for laugh, we run into trouble deciding whether U changes to or E in Gachai. But if we develop a model to actively check whether the reflexes are derivable from the reconstructions, the model should, in principle, learn to not predict an U here. We call this approach daughter to proto to daughter, or DPD. The proto-to-daughter part is called reflex prediction, and there has been work on how to model this computationally. One way is to use a sequence-to-sequence transduction model with a target language token attached to the input protoform to specify which daughter language to predict the reflex for. We proposed the DPD architecture to implement the DPD workflow end-to-end. It has two submodels, a daughter-to-proto-reconstruction submodel called D2P, and a proto-to-daughter reflex prediction submodel called P2D. Both of these are encoder-decoder sequence-to-sequence transduction models. What we want to do here is to feed predicted reconstructions from D2P into P2D and have P2D propagate its losses all the way back into D2P. This requires a differentiable connection between D2P and P2D, so we use a dense bridge network to connect the final layer decoder state from D2P to the encoder input of P2D. During training, we consider 5 losses. For label cognate sets, we can enforce a supervised cross-entropy loss as usual on both submodels. Regardless of whether a label is available, we can feed reflexes into D2P and forward propagate it all the way through the DPD model to get reflex prediction outputs from P2D. Then we use cross-entropy loss on the recovered reflexes to train the entire DPD network. Additionally, when we do have the protoform label, we can check if D2P made an incorrect protoform prediction, in which case we might not want P2D to then recover the reflexes correctly from an incorrect input. For those cases, we treat correct reflexes as negative examples and use the cringe loss to lower the probability of each negative token. More detail in the paper. Finally, notice that P2D takes both the bridge network's output and the actual embeddings of the Go protoform. To make these two representations consistent, we apply a cosine similarity loss between them. The overall loss is calculated as a weighted sum of all of these losses. To test how well DPD performs, we set up a few baselines. A strawman approach is to simply ignore the unlabeled data and perform supervised training on the limited labeled data. We call this the supervised-only strategy. Then we have two established semi-supervised learning approaches. The first one is bootstrapping. This involves adding the model's most confident predictions for unlabeled inputs back into training set as pseudo-labels. The second one is the pi model, which feeds two stochastically augmented inputs from the same training example and applies a mean square difference loss between the outputs as a form of consistency regularization. Because phonemes are discrete and randomly changing phonemes could make sound changes irregular, we propose to implement stochastic augmentation by randomly reordering the reflexes in the input and then probabilistically dropping a daughter language. Some of these strategies, together with DPD, are not mutually exclusive. DPD and pi model can be used in tandem, and bootstrapping can be used on top of any other strategy involving unlabeled data. In total, we experiment with 8 strategies. We consider the combination of pi model and bootstrapping to be a strong baseline. DPD leaves the architecture of the submodels up to implementation. We test both GRU and transformer, forming a total of 16 strategy architecture combinations. We use Chung et al.'s Wikihan dataset for Middle Chinese reconstruction and the phonetic version of Maloney et al.'s Romance dataset for Latin reconstruction. Both datasets come fully labeled. To create a semi-supervised dataset, we randomly remove a fixed percentage of the labels. We focus on datasets retaining 10% of the labels. This translates to 607 labels for Romance and 362 labels for Wikihan. As creating such a dataset is a random process, we perform the same experiment with 4 different dataset seeds. For evaluation, we use accuracy, token edit distance, token error rate, which is a length normalized token edit distance, feature error rate, a length normalized measure of phonetic edit distance, and finally B-cubed F-score to measure structural similarity. What we find is that strategies involving DPD perform quite well. For 10% labeled Wikihan, DPD with pi model and bootstrapping performs the best for both architectures. Transformer trained with DPD on its own performs similarly well, and these are significantly better than all baselines. On Romance, Transformer performed best when trained with DPD with pi model and bootstrapping, while GRU performed the best when trained with DPD with bootstrapping, both of which are significantly better than all baselines. In the paper, we also vary the proportion of label data in the train set and see that DPD can usually generalize to other labeling settings. We perform various analyses, but I'm only going to highlight an interesting one. Using hierarchical clustering, we compare the phoneme embedding learned by the most accurate DPD-based model versus their non-DPD counterpart. For French, we see a clear division between the vowels and consonants in the DPD-based model, but less so for the non-DPD model. We also see that the DPD model is good at grouping together consonants that differ only in one feature, such as voicing. For Cantonese, we additionally observe that tones are clustered more closely together by the DPD-based model. We conclude that DPD-based strategies are good at capturing linguistically meaningful representations of phonemes. In the paper, we present additional analysis such as the interaction between D2P and P2D during training, errors made by DPD versus non-DPD models, transductive evaluation, ablation studies removing the unlabeled data, and supervised reconstruction with DPD. To sum up, we introduced the new task of semi-supervised protoform reconstruction. We believe that this brings us a step closer towards building practical automated protoform reconstruction systems that can assist early-stage proto-language reconstruction projects. Informed by the comparative method, we proposed the DPD architecture for this task. We show that DPD learns effectively from unlabeled data and achieves performance better than existing sequence-to-sequence reconstruction models and established semi-supervised learning techniques. That's the end of my presentation. You can find links to our paper, code, and checkpoints on the slide. Thank you.